When scientists at NASA received the first atmospheric data from an exoplanet photographed by James Webb Space Telescope, one researcher reportedly stood up from his desk, walked out of the room, and didn't come back for 20 minutes. When he returned, all he said was, "We need to check the instruments again. This doesn't make sense." But the instruments were fine. The data was real. And what James Webb had just revealed about this alien world orbiting a star 700 light years away wasn't just unexpected. According to everything we thought we knew about planetary formation and atmospheric chemistry, it was impossible. And yet, there it was, staring back at them from the most detailed exoplanet image ever captured. What you're about to hear isn't just another space discovery. This is the moment we realize that alien planets are far stranger, far more complex, and far more interesting than our best models ever predicted. Look, I know what you've seen online. The headlines screaming that James Webb captured the first real image of another planet. And yeah, that's technically not true. We've been photographing exoplanets since 2004, getting blurry, pixelated dots that barely told us anything beyond, yes, there's something there. But here's what those headlines got wrong, and why the real story is actually way more exciting. James Webb didn't just take a better picture. It fundamentally changed what we can learn from looking at these distant worlds. It's the difference between seeing a house from a mile away and actually walking inside, turning on the lights, and reading the thermostat. Webb isn't just seeing exoplanets. It's analyzing them, dissecting them, and revealing details about alien atmospheres that we had no right to expect we'd ever be able to detect. And some of those details are keeping astronomers up at night. Before we dive into what Webb found that has scientists so confused, I need you to do something for me. Hit that subscribe button right now. Here at the Space Frontier, we're breaking down the latest discoveries from James Webb, NASA missions, and deep space observations in a way that actually makes sense, without the hype and without the BS. We've got videos coming up about what Webb just detected around distant stars that has astrobiologists completely rethinking the search for life, and you're not going to want to miss that. So subscribe, hit the bell, and let's keep going because this story gets wild. All right, so let's set the stage. For decades, finding planets around other stars was like trying to spot a firefly next to a searchlight from 1,000 miles away. The star is so bright, and the planet is so small and dim that directly photographing it seemed nearly impossible. That's why most exoplanets we've discovered, and we're talking about over 5,000 confirmed worlds now, were found indirectly. We watched stars wobble from gravitational tugs. We measured tiny dips in starlight when planets passed in front of their suns. These methods told us planets were there, how big they were, how close to their stars they orbited. But they didn't show us the planets themselves. Not really. Then, in 2004 and 2008, astronomers managed to capture the first direct images of exoplanets using massive ground-based telescopes, and eventually the Hubble Space Telescope. And honestly, they were disappointing. Fuzzy dots, blurry smudges of light. You could tell something was there, but you couldn't learn much from it. Scientists could estimate the planet's temperature based on its infrared glow, maybe get a rough idea of its size, but that was about it. The atmospheres, the weather, the chemistry happening in those alien skies, totally out of reach. It was like looking at Earth from another solar system and only being able to say, yeah, there's a blob there and it's kind of warm. Not exactly the stuff of groundbreaking science. Enter James Webb Space Telescope. Launched in December 2021 and beginning science operations in mid-2022, Webb was designed from the ground up to see the universe in infrared light. And here's why that matters. Infrared is essentially heat radiation. Everything that has a temperature above absolute zero emits infrared light. Stars blast out infrared along with visible light. But planets, especially giant gas planets that are still cooling from their formation, emit their own infrared glow. And infrared light can pass through cosmic dust and gas that would block visible light completely. So when Webb points its massive mirror and ultra-sensitive instruments at an exoplanet, it's not just taking a picture. It's reading the planet's heat signature. It's detecting the specific wavelengths of light absorbed by different molecules in the atmosphere. It's essentially doing spectroscopy, breaking down the light into a chemical fingerprint that tells us exactly what gases are present. Now here's where it gets crazy. One of the first exoplanets James Webb observed in detail is a world called HIP 65426b. This thing is a monster. It's a gas giant about 6 to 12 times the mass of Jupiter, orbiting a star roughly 385 light-years from Earth. It's young, maybe only 15 to 20 million years old, which in cosmic terms is basically a newborn. And because it's young, it's still hot from its formation, glowing brightly in infrared. Perfect target for Webb. When the telescope captured direct images of HIP 65426 Ia in multiple infrared wavelengths, astronomers got their first truly detailed look at an exoplanet's atmosphere in action. And immediately, things got weird. The atmospheric composition didn't match the models. Scientists expected to see certain ratios of methane, water vapor, carbon monoxide, carbon dioxide, all the usual suspects you'd find in a giant planet's atmosphere. But the ratios were off. Some chemicals were more abundant than predicted, others were nearly absent when they should have been common, and the temperature distribution across the planet's atmosphere showed patterns that our current understanding of atmospheric dynamics couldn't fully explain. It was like opening a chemistry textbook and finding all the equations had been rewritten. Now, I want to be clear here. This doesn't mean the laws of physics are broken. It means our models of how giant planets form, how their atmospheres evolve, and how chemistry works under extreme alien conditions are incomplete. And that's actually more exciting than finding exactly what we expected, because it means there's something new to learn. But wait till you hear this. Webb didn't stop at HIP 65426b. It turned its instruments toward another exoplanet, a world called WASP 39b, located about 700 light years away. This one's different. It's a hot Saturn, a gas giant roughly the mass of Saturn, but orbiting incredibly close to its star, completing a full orbit in just about 4 days. Because it's so close to its star, the planet is roasted to temperatures exceeding 1,600 degrees Fahrenheit. The atmosphere is constantly being blasted by intense radiation, and when Webb analyzed the light filtering through WASP 39b's atmosphere as the planet passed in front of its star, it detected something nobody was quite ready for: carbon dioxide. Clear, unambiguous, detailed detection of CO2 in an exoplanet's atmosphere. First time ever. Now you might be thinking, okay, cool, carbon dioxide, so what? Here's the so what. Detecting specific molecules in exoplanet atmospheres with this level of confidence and detail means we can now start asking questions that were pure science fiction just a decade ago. We can figure out how atmospheres form and change over time. We can identify planets with chemical imbalances that might indicate biological processes, the kind of disequilibrium chemistry that on Earth is caused by life. We can study weather patterns, cloud formation, atmospheric escape, how planets lose their air to space over billions of years. James Webb turned exoplanet science from astronomy into chemistry, meteorology, and potentially even biology. That's the revolution. And here's the thing that has scientists both excited and slightly freaked out. Another planet. Webb observed, VHS 1256b, showed evidence of silicate clouds. We're talking clouds made of tiny particles of vaporized rock and minerals, drifting through an atmosphere so hot that rocks don't just melt, they evaporate and then condense into clouds like water does on Earth. The temperature on this world reaches over 1,500 degrees Fahrenheit, and the atmosphere is turbulent, chaotic, with clouds of liquid rock droplets swirling through skies that would vaporize anything we've ever built. And Webb can see it. Webb can measure it. Webb can tell us what minerals are in those clouds based on their spectroscopic signatures. And that's not just a better picture. That's reading the weather report on an alien world 40 light years away. So why does any of this matter? Why should you care about the atmospheric chemistry of gas giants hundreds of light years from Earth? Because every one of these planets is a laboratory, a natural experiment in planetary science that we can study to understand how planets, including our own, form and evolve. Earth didn't start out with the atmosphere we breathe today. It took billions of years of geological processes, chemical reactions, and yes, the emergence of life to create the air we depend on. By studying the atmospheres of exoplanets in different stages of development, orbiting different types of stars, experiencing different levels of radiation and heat, we're building a comprehensive understanding of how planets work, and that knowledge has direct implications for one of the biggest questions humanity has ever asked. Are we alone? Here's what keeps astrobiologists up at night, and this is the big one. James Webb has the capability to study not just giant gas planets like the ones I've been talking about, but also smaller rocky worlds more like Earth, planets orbiting in the habitable zone of their stars, where temperatures might allow liquid water to exist on the surface. And if Webb can detect carbon dioxide, methane, water vapor, and other gases in the atmospheres of giant planets, it can potentially do the same for rocky planets. And if it finds certain combinations of gases, certain chemical signatures that don't make sense unless there's an active biological process producing them, well, that's when things get really interesting. We're not there yet. The technology is still being refined, the targets are being identified, the observation time is being carefully allocated, but the possibility is real. Within the next few years, James Webb might detect biosignature gases in the atmosphere of a rocky exoplanet, and if that happens, everything changes. Now, I need to hit pause for a second and talk about what's actually happening here versus what the internet wants you to believe. Did James Webb capture the first image of an exoplanet? No, that happened years ago. Is Webb's imaging technology better than anything we've had before? Absolutely. But the real breakthrough isn't the pictures, it's the data, it's the spectroscopy. It's the ability to break down light into its component wavelengths and read the chemical story those wavelengths tell. A picture of an exoplanet is cool, a detailed chemical analysis of its atmosphere that reveals unexpected compounds and forces us to rethink planetary formation models. That's groundbreaking. That's the difference between a postcard and a scientific revolution. And here's something that doesn't get talked about enough. Every single one of these observations, every spectrum Webb captures, every molecule it detects, is adding to a growing database of exoplanet characteristics that future scientists will use to refine models, test hypotheses, and make predictions. We're building the periodic table of planets. We're cataloging the diversity of worlds that exist in our galaxy. And just like the periodic table of elements revealed patterns that led to deeper understanding of atomic structure and chemistry, the catalog of exoplanet atmospheres is going to reveal patterns we can't even anticipate yet. We're at the very beginning of this process. The data is just starting to come in, and already it's weirder and more complex than anyone expected. So let me ask you something, and I genuinely want to know your answer. Drop it in the comments below. When James Webb eventually analyzes the atmosphere of a rocky, Earth-sized planet in the habitable zone and finds a mix of gases that could indicate life, what do you think happens next? Do we send a message? Do we build bigger telescopes to study it in more detail? Do we just sit with that knowledge and let it change how we see our place in the universe? I'm curious what you think, so let's get a conversation going in the comments. Seriously, scroll down right now and tell me your take. I read every single comment. All right, back to the science. One of the most fascinating aspects of Webb's exoplanet observations is what they're revealing about planetary diversity. Before we started finding exoplanets in the 1990s, our only reference for what a solar system looks like was our own. Small rocky planets close to the sun, gas giants farther out, everything in relatively circular orbits. Nice and orderly. Then we started discovering hot Jupiters, massive gas giants orbiting closer to their stars than Mercury orbits our sun. We found super-Earths, rocky planets bigger than Earth but smaller than Neptune, a category that doesn't even exist in our solar system. We found planets orbiting binary stars, planets with wildly elliptical orbits, rogue planets drifting through space with no star at all. The universe, it turns out, is way more creative than we gave it credit for. And now, with James Webb giving us detailed atmospheric data, we're discovering that the diversity doesn't stop at orbital characteristics and size. The atmospheres themselves are wildly different from planet to planet, even among worlds that seem similar on paper. Some gas giants have atmospheres dominated by water vapor. Others are rich in methane or carbon monoxide. Some have thick cloud layers that completely obscure the lower atmosphere. Others are relatively clear. The temperature structures vary. The chemical compositions vary. And in many cases, the variations don't match what our models predict based on the planet's mass, distance from its star, and the star's characteristics. There's something else going on, additional factors we haven't fully identified yet, that influence how these atmospheres develop and behave. This is the part where I need to share something that a lot of science communicators don't talk about enough. Science isn't a collection of facts. It's a process. It's asking questions, gathering data, building models, testing those models, finding out where they break, and then refining them. Every time James Webb finds an exoplanet atmosphere that doesn't fit the predictions, that's not a failure of science. That's science working exactly as it should. We make our best guess based on current understanding, we test it against reality, and reality teaches us something new. The fact that these exoplanet atmospheres are surprising us means we're learning. And what we're learning is that planets are more complex, more varied, and more interesting than we ever imagined sitting around theorizing with only our own solar system as a reference. Here's another thing that blows my mind. The light that James Webb is analyzing, the infrared photons hitting its mirrors and instruments, left those exoplanets hundreds of years ago. When the light now being detected from a planet 700 light years away began its journey toward us, it was the early 1300s on Earth. The Renaissance hadn't started. The Americas hadn't been discovered by Europeans. Entire civilizations rose and fell in the time it took that light to cross the gulf of space between there and here. And now, in 2024, we're using that ancient light to decode the atmospheric chemistry of a world so distant that even traveling at the speed of light, it would take 7 centuries to reach it. That's not just science, that's almost magic. It's using the universe's own messenger, light, to tell us stories about places we will never physically touch. Now let me tell you about one more planet that Webb has observed, and this one's a personal favorite. It's called WASP 96b, a gas giant about half the mass of Jupiter, located roughly 1,150 light years from Earth. When Webb analyzed the spectrum of light passing through its atmosphere, it detected clear signatures of water vapor, along with evidence of clouds and haze. But here's the kicker. The amount of water detected was higher than expected, and the clouds showed unusual properties that suggest complex atmospheric chemistry and possibly active weather systems. This is a planet where it might rain liquid metals, where the wind speeds could exceed anything we've ever measured on Earth. where the day side is scorching hot, and the night side, if the planet is tidally locked to its star, might be comparatively cooler, creating massive temperature-driven storms. And we can study all of this from over 1,000 light years away, using nothing but light and some really, really smart science. So here's where we land. Did James Webb capture the first real image of another planet? No, and anyone telling you that is either misinformed or trying to get clicks. But did James Webb revolutionize our ability to study exoplanets, turning them from distant dots of light into detailed worlds with measurable atmospheres, temperatures, and chemistry? Absolutely. 100%. No question. This is the telescope that turned exoplanet science from "we know they're there" to "we know what they're made of and how they behave." And we're just getting started. Webb has decades of operational life ahead of it, potentially. Every year, it's going to observe more exoplanets, gather more data, refine our understanding, and probably surprise us a few more times with discoveries that don't fit the models. And that brings me to the bigger picture. The reason this matters, the reason you should care, is because understanding planets, how they form, how they evolve, what makes them habitable or hostile, is ultimately about understanding our own world and our place in the cosmos. Earth is one data point, a sample size of one. For all of human history, it was the only planet we could study in detail. Now, thanks to missions like James Webb, we have hundreds of data points. We're comparing notes, we're seeing what's common and what's unique. And every discovery, every unexpected atmospheric composition, every weird weather pattern on a world 500 light years away teaches us something about the processes that shaped our own planet and the conditions that allow life to thrive here. If you found this video as mind-blowing as I did putting it together, do me a huge favor and share it. Send it to someone who loves space, post it on your socials, help spread the word about what's actually happening out there in the universe. The more people who understand and appreciate this science, the more support there is for future missions, for continued funding, for the next generation of telescopes that will go even further than Webb. And honestly, the cooler our collective future becomes when we're all on the same page about just how incredible the universe is. The Space Frontier is here to bring you the real stories behind the headlines, the actual science without the hype, and the discoveries that genuinely matter. We've got videos coming up on what Webb is finding in the early universe, the bizarre objects lurking in deep space that challenge everything we thought we knew, and the missions NASA is planning for the next decade. Make sure you're subscribed so you don't miss any of it. And seriously, drop a comment. Let's talk about this. What exoplanet discovery are you most excited about? What question do you want Webb to answer next? I'm here for it, and I love hearing from you all. So here's the bottom line. James Webb didn't capture the first image of another planet, but it did give us the first real look at what those planets are actually like. And what they're like is strange, diverse, complex, and absolutely fascinating. We're living in the era where humanity stopped wondering if there are other worlds and started studying them in detail. That's the story. That's the revolution, and it's happening right now. Thanks for watching, and I'll see you in the next one. Keep looking up.